Hello guys, here actually I want to calculate the integration dx e to the power minus x square. Right, in the previous talk we calculated it using the definition of gamma functions, but here we assume that we don't know the definition of gamma functions and we have some basic math knowledge. Then how we can get this? Okay, that is our aim. So that means as e to the minus x square is the even function, so we can write this integration 0 to infinity dx equals to minus infinity to plus infinity e to the minus x square and half of this, right? Because it is the even function, so this is actually equals to the minus infinity to 0 dx e to the minus x square, right? So that is the case. So we start with this actually. We start with minus infinity to plus infinity dx e to the minus x square, and we let me take it as I. So we name it as I. Okay. I suppose most of you know that about the Cartesian coordinate and polar coordinate because this knowledge is necessary for this derivation. So in the Cartesian coordinate, there in x and y, these variables, they are independent, and so this I is actually expressed in terms of x. We can also express it in terms of dy. Doesn't matter, both are the same, right? And this is also I, right? So what is I square? So you can write it actually to the minus infinity dx dy e to the minus x square plus y square, right? Now, why do we have to do this? Okay, that's the thing that we need to know, because we have a knowledge of polar coordinate where you know the point that means in Cartesian coordinate when the we locate the point with respect to x and y. In polar coordinate we define this point in terms of two variables r and theta. Okay, r and theta. R is the distance from origin, right? This, and theta is the angle between the x and this r, radial distance. Okay, and you know that when using the Pythagoras equation, that is very straightforward. This x square plus y square is actually r square, right? So this x square plus y square is r square. So as you know that, so we can use this actually here. So that is our aim, and that is the reason we are actually multiply this. We express it as I square instead of r. So okay. So if we know this I square, we easily get the square root of this is I. So there is no problem. But their advantage is we can replace it x square plus y square with r. But when we replace this, then there will be change in the area element, because dx and dy, that will also change. But what if dx and dy, right? That we need to know, and that probably know also, because this is x, this is y, and what we do is there is a point x and y, and there is a small change in x and small change in y. This is dy and this is dx. That means just for the better visual understanding, I just that means draw it in a larger in a longer length scale, but it is actually a very small element. Okay, so this is dx and dy, and this area is dx into dy. So what is the equivalent of this area element in the polar coordinate? So in the polar coordinate, so again there is this point R, this is the distance R, and then we change the angle with the infinitesimal and which is d theta, and so this is R, and you change this radial distance with a small angle d theta, and there is a change in the radial distance. So, and this is actually dr. Okay, this is a small change in radial distance dr. Okay, so the volume element is this. I think most of you understand this. This is the volume element. Okay, there is a small change in radial distance, small change in angle. Okay, and what is the distance? What is the value of this length? Right? We know that is actually R into d theta. So this is actually R into d theta. Okay. So therefore, what is the area of this volume element? This is actually this into this. So that means R d theta into dr. Okay. I hope that you all understand this. So the dx and dy, this is equivalent to R dr d theta. And one thing I want to mention it, I should mention it here, that the R is a radial distance irrespective of any direction. So that means if you go there also, if the and this is then within the circle, any point within the circle have a coordinate R. Okay, and the theta, of course, you can see it is actually a full circle. So that means it can go from, if this is R, so the theta is 0, and you can go with the full circle. So this will be 2 pi. So it actually varies from 0 to, here it is pi, and here 2 pi. Okay, so it varies from 0 to 2 pi. So R is from 0 to infinity, and theta is from 0 to 2 pi. I think everybody understands this. Therefore, we can write this I square. Okay, then we write it all and write it again. So this is actually dx dy e to the power minus x square plus y square. We can write it actually from d theta r dr, and theta is from 0 to 2 pi, and r is from 0 to infinity, and this x square is replaced with r square. Okay, as you know, r and theta, they are independent as usual. So the theta integration can be done easily, and it is given is 2 pi, right? There is no problem with that. And to do this integration, we can write it like dr square into half e to the power minus r square. Why we are writing this? Because if we take r square equals to u, then it will be just du e to the power minus u, right? So this is just an exponential integration. So you can also do that, like you can take r square equals to u, and like 2r dr equals to du, and you replace there, and you can get this. But you can also that will write it like that way. That means that's the you do, and this is the pi, and this is just the integration of du e to the minus u. Okay, and this is pi, this is minus of u, 0 to infinity, right? And the value of this is 1. Okay, I think up to this point we understand what I have done here, and therefore the I square is actually pi. Okay, therefore our target is to get the I, and therefore I is root over pi. Okay, so therefore we can write the e to the minus into plus infinity dx square equals to root over pi, and so equivalent is 0 to infinity dx e to the minus x square is root over pi by. So that is the standard Gaussian integration, and I hope you will understand that how you can get that in a straightforward manner. Okay, thank you.